In the summer of 2019, a grizzly bear in the Yellowstone ecosystem that researchers had been tracking for 11 years did something that stopped a team of wildlife biologists cold. The animal, a large male designated by the study as Bear 399's male contemporary in the northern range, returned, after an absence of 3 years, to a specific pullout along a highway corridor where visitors had, years earlier, been feeding bears from car windows. The feeding had stopped. The rangers had cracked down. The pullout had been closed, reopened, modified, and the human behavior there had changed completely. But the bear came back. It approached the same stretch of road at the same time of year, moved along the same corridor, and demonstrated, through its behavior and its positioning, that it remembered exactly where humans had once provided food. 3 years. No reinforcement. No reason to return from a strictly caloric standpoint, because the food was gone and had been gone for a long time. The bear remembered anyway. The researchers who documented that return spent months arguing about what it meant. Not about the observation itself, which was clear in the GPS data and in the direct field observations, but about what category of cognitive phenomenon it represented. Was it episodic-like memory, the kind of structured recollection of specific past events that we associate with higher cognitive function? Was it something more diffuse, a landscape-level spatial memory that incorporated human infrastructure as a persistent feature of the territory map? Was it something in between, a form of associative learning so robust and so well consolidated over years of reinforcement that it survived years of absence and redirected the animal's seasonal movements across a landscape measured in hundreds of square miles? The argument was productive and unresolved, and pointed toward a body of research on grizzly bear cognition that has been accumulating for 2 decades, and that most people who live adjacent to grizzly country, recreate in it, or make policy about it, have never encountered. If any of what you are about to hear changes how you think about the animal at the top of North America's food chain, and it should, then stay with this. There is more coming that is worth your time. The thing that makes the grizzly bear memory question so consequential and so underappreciated is that it sits at the intersection of 2 problems that both matter enormously and that are almost never discussed together. The first problem is human safety in grizzly country, which is the problem that gets most of the public attention and most of the policy bandwidth whenever a bear mauls a hiker or raids a campground or appears too close to a trailhead at the wrong time of year. The second problem is grizzly bear conservation, which is the problem that gets most of the scientific attention and most of the advocacy energy and most of the legal action from conservation organizations, trying to keep the Endangered Species Act protections that have allowed the Yellowstone and Northern Continental Divide populations to recover from near extinction in the 1970s. What the memory research connects, in a way that is genuinely surprising and that the scientists involved did not fully anticipate, is that these 2 problems are not separate. They are expressions of the same underlying biological reality. Understanding how grizzly bears remember human settlements, food sources, and conflict zones with what researchers have increasingly described as human-scale fidelity is not just an academic exercise in cognitive ecology. It is the key to understanding why human-grizzly conflict has the spatial and temporal patterns it has, why certain management interventions work and others demonstrably do not, and why the expansion of the grizzly's range in the coming decades, which is happening right now at the edges of the recovered populations, is going to produce a collision between bear memory and human infrastructure that nobody is adequately prepared for. Start with what the memory research actually found, because the findings themselves are the most important thing to establish clearly before anything else. The foundational work came from a series of studies conducted across the Yellowstone ecosystem beginning in the early 2000s, using GPS collar data from a population of grizzlies that had been under intensive monitoring since the late 1970s. The researchers were not, initially, studying memory. They were studying movement ecology, specifically the questions of how grizzlies navigate their home ranges, how they respond to changes in food availability across seasons, and how their movement patterns intersected with the road network and human development within and adjacent to the park boundary. What they found in the movement data was a pattern that was not predicted by the existing models of large carnivore spatial behavior, and that required an explanation that the existing models could not supply. Individual bears showed extremely high fidelity to specific locations associated with past food acquisition events, including events that had occurred years earlier. The fidelity was not just to broad habitat types or to elevational zones where food was generally available. It was to specific drainage corridors, specific clearings, specific road segments, specific campground areas, specific ranch boundary zones. Bears returned to these places with the kind of spatial precision that implied not just a general memory of the landscape, but a detailed, location-specific memory of where particular food rewards had been obtained. And the critical finding, the one that the researchers initially thought might be a data artifact before confirming it across multiple individuals and multiple years, was that this fidelity persisted through periods of absence that stretched to 3, 4, and in some documented cases, more than 5 years. Bears that had not been in a specific location for half a decade returned to it during the seasonal window, when the food that had originally attracted them would have been available, or in the case of human-associated food, would have been available in the past. The implications of that finding take a moment to absorb because they are not intuitive against the backdrop of how most people think about animal cognition. We are accustomed to thinking about animal memory in terms of the relatively short-term associative learning that dominates the cognitive ecology literature on most species. A bear learns where food is. It returns. If the food is gone long enough, the association weakens and the behavior extinguishes. That is the standard model. What the Yellowstone data was showing was something substantially more persistent. The memory that was driving the return behavior was not extinguishing on the timescale that the standard model predicted. It was surviving years of absent reinforcement and continuing to influence movement decisions at landscape scale. The bears were not just remembering that food had been somewhere. They were remembering where, with a spatial specificity that allowed them to navigate directly to the location years later. And they were remembering when, timing their returns to the seasonal window associated with the original food event. The research team, led by scientists at the USCA's Northern Rocky Mountain Science Center, in collaboration with colleagues at Utah State and the University of Calgary, coined a phrase to describe what they were seeing that has since circulated widely in the applied wildlife management literature and almost not at all in public science communication. They called it landscape-level episodic-like memory, and the like qualifier is doing important scientific work in that phrase. It is not claiming that grizzly bears have the fully human form of episodic memory, the richly narrative, consciously accessible recollection of specific past events with detailed contextual embedding that cognitive scientists have argued is unique to, or at least most fully developed in humans. It is claiming that grizzly bears have a functional analog, a memory system that operates on similar timescales, encodes similar levels of spatial and temporal specificity, and drives behavior in ways that functionally resemble what episodic memory does in human cognition. The distinction matters scientifically. The practical implication does not depend on resolving it. Whether the bear is remembering in the human sense or in a functional analog of the human sense, the behavior is the same. It returns. It knows where. It knows when. It will keep returning. The field of comparative cognition has been slowly assembling the evidentiary foundation for understanding why this might be the case for grizzlies specifically. And the picture that emerges is one that makes the memory capacity less surprising the more you understand about the ecology of the species. Grizzly bears are omnivores with a dietary breadth that is, among large North American mammals, essentially unparalleled. In a single year, a grizzly in the Yellowstone ecosystem may exploit more than 200 distinct food items, ranging from cutworm moths gathered in alpine screes in late summer to cutthroat trout intercepted at spawning runs in spring, to whitebark pine nuts cached by squirrels and excavated by bears in fall, to ungulate carcasses available in varying locations and seasons throughout the year, to an enormous variety of forbs, berries, roots, and insects distributed across a home range that in the case of adult males can exceed 2,000 square kilometers. The logistical challenge of exploiting a resource base that is this spatially distributed, this temporally variable, and this dependent on anticipating where specific foods will be available in specific windows of the year is a cognitive challenge of a specific kind. It selects hard for memory systems that can store large numbers of location-specific food events, retain them over the full annual cycle and across multiple annual cycles, and retrieve them with enough temporal precision to get the animal to the right place at the right time. This is the ecological logic of the memory capacity that the researchers were documenting. The grizzly's brain has been shaped by selection pressures that favor exactly the kind of long-duration, spatially precise, temporally structured memory that the GPS data was revealing. The bear that remembered, 5 seasons later, that a particular whitebark pine grove on a specific south-facing slope produced an exceptional mast crop in a good year, and returned to it in the appropriate fall window, was not performing a cognitive feat out of proportion to its ecological niche. It was doing exactly what its ecology demands. The same memory system that tracked the grove also tracked the campground. The same system that stored the moth aggregation site also stored the ranch boundary where elk gut piles accumulated during hunting season. The same system that encoded the berry meadow also encoded the highway pullout where a tourist handed food through a car window 3 years ago. The human settlement is not a special category in the grizzly's memory architecture. It is one more food source location in a landscape-scale memory map that the animal maintains with the same fidelity it applies to every other resource in its ecological world. That single insight, that human food sources are not special categories for grizzly memory, but are entries in the same high-fidelity memory system the animal uses for its entire resource landscape, is the one that the scientists who study human-grizzly conflict say changes everything about how conflict should be managed. And it is the one that is almost entirely absent from the public conversation about grizzlies, from the news coverage of conflict incidents, from the educational materials distributed at park entrances, and from the policy frameworks that govern how wildlife managers respond to bears that have become, in the official language, food-conditioned or habituated to human presence. The official framework treats food conditioning as a behavioral state that can be addressed through removal of the specific animal or through removal of the attractant that produced the conditioning. The memory research suggests that the framework is missing something fundamental. The conditioning is not just a current behavioral state. It is a memory trace that is recorded with remarkable durability, that persists through management interventions that remove the animal or the attractant, and that will redirect the animal's behavior for years, potentially for the rest of its life, toward the location where the food was obtained. The management implications of that gap between the official framework and the research findings have played out in documented cases that are painful to examine because of what they reveal about how predictable the outcomes were, given what the research was showing. The pattern is consistent enough to describe in general terms without needing to attribute blame to any specific agency or individual. A bear obtains food reward from a human source, whether through improperly stored garbage, agricultural crops, livestock, or direct provisioning by humans who are unaware of or indifferent to the consequences. The bear is captured, relocated, perhaps fitted with a GPS collar. The attractant is, ideally, removed or secured. The bear returns, often to the same drainage, often within a season, sometimes within weeks. Wildlife managers, operating from the behavioral extinction model, interpret the return as evidence of a particularly persistent or motivated individual. They relocate the bear again, sometimes to a greater distance. The bear returns again. Eventually, the bear is killed. The case is closed. A new bear eventually discovers the attractant, whether the same one that was never fully secured or a new one that has developed in the interim. The cycle begins again. The management intervention that would actually address the problem, which is preventing the initial memory formation by eliminating the attractant before the bear has multiple reinforced exposures to it, is also the hardest one to implement because it requires changing human behavior proactively rather than reactively. And proactive behavior change is the most difficult kind to produce in any regulatory context. The relocation failure rate in documented grizzly conflict cases is one of the least discussed statistics in wildlife management and one of the most informative. Studies examining the outcomes of bear relocations in the Yellowstone and Northern Continental Divide ecosystems have consistently found that bears with established food conditioning histories return to their capture area or to similar human-associated attractants at rates that are far higher than the rates for bears relocated for other reasons. A bear relocated for displacing prey kills from other bears comes back at a lower rate than a bear relocated for raiding a chicken coop. The difference is not explained by relocation distance, by the age or sex of the animal, or by any of the demographic variables that managers typically consider. The difference is explained by what the animal remembers and how durable that memory is. The food-conditioned bear has a specific, high-fidelity memory trace, pointing to a location associated with high caloric reward. That memory trace is driving its movement decisions. Moving the animal does not erase the memory. It just creates a navigational problem for the animal to solve. And grizzlies, with their well-documented spatial navigation abilities and their landscape-scale home range knowledge, are equipped to solve navigational problems. There is a specific body of data from the Yellowstone ecosystem that illustrates this point with unusual clarity, and that the researchers involved have described as among the most sobering findings of the multi-decade monitoring program. Following the reintroduction of wolves to Yellowstone in 1995 and the subsequent changes in elk behavior and distribution that wolf predation produced, grizzly bears in the northern range of the park shifted their spring foraging behavior substantially, increasing their use of wolf kill carcasses as an early-season food source before vegetation became abundant. The spatial pattern of this shift was tracked through GPS collar data across dozens of individuals over more than 15 years. What the data showed was a striking divergence between individuals that had prior experience with wolf kill carcasses and individuals that encountered them for the first time. Bears with prior experience located carcasses faster, visited them more efficiently, and derived more caloric benefit per unit of search effort than naive animals. They knew where to look because they remembered where kills had been before. Wolf predation in the northern range is not randomly distributed. Wolves use terrain features, prey movement corridors, and hunting ground preferences that are partially consistent across years. A grizzly that had exploited wolf kills in the northern range for several years had a landscape-scale memory map of where elk were likely to be killed during specific seasonal windows. It used that map, The naive animal without the memory map was less efficient. The memory was not just a record of past food events. It was a predictive model of future food distribution, built from remembered past events, that the bear was using to navigate a dynamic resource landscape. The same predictive quality of the grizzly's spatial memory is precisely what makes human settlements so problematic as memory-recorded food sources. A human settlement is, from the perspective of a grizzly bear's foraging logic, one of the most predictable and highest-density food aggregations in its landscape. Garbage accumulates on a schedule. Fruit trees produce in a predictable seasonal window. Chickens are where they were last time. Apiaries persist from year to year. The caloric density of a successful raid on a human food source is exceptional by the standards of wild foraging. A bear that has raided a beehive 3 times in 3 years has formed a memory of a high-value, reliably located, seasonally predictable food source that ranks among the most compelling entries in its landscape memory map. The predictability of human food sources, the characteristic that makes them attractive to bears in the first place, is also the characteristic that makes the memory of them extraordinarily persistent. High value, reliable, repeated rewards produce the most durable memory traces. Human settlements provide exactly that reward structure. The genetic dimension of what the memory research revealed is the part that surprised the scientists most, and that has the most profound implications for how grizzly bear populations will interact with human infrastructure as they expand their range in the coming decades. The Yellowstone Monitoring Program has, over its 4-decade history, assembled a genetic database of the bears in the ecosystem that is detailed enough to trace maternal lineages across multiple generations, and to examine whether behavioral traits, including the tendency to associate with human food sources, show patterns consistent with either genetic transmission or behavioral transmission through social learning. The findings on this question are still being developed, but the current weight of evidence suggests something that researchers have been careful to state conservatively, and that the public conversation has not yet absorbed. Food-conditioned females in the Yellowstone population are more likely to produce offspring that also become food-conditioned than non-food-conditioned females, and this pattern persists even when the offspring are not observed directly accompanying the mother during food conditioning events. The pattern is consistent with both genetic transmission of risk-tolerance traits that predispose bears to human proximity and with behavioral transmission through the cubs accompanying the mother during her landscape movements and learning the locations of human food sources as part of their education in the resource geography of their natal range. Both mechanisms are likely operating simultaneously, and distinguishing their relative contributions is methodologically challenging. What is not challenging to establish is the practical implication. A food-conditioned female grizzly is not just a problem for the individual conflict incidents she produces. She is a problem across the generations she produces, and through them, across the portions of the landscape they occupy. Her cubs learn the landscape she knows. They learn where the food is. They record those locations in the same high-fidelity memory system their mother used to record them. When they disperse and establish their own home ranges, they carry those memories with them. They may encounter new human food sources in their dispersal areas and add those to the existing map. The conflict geography that a food-conditioned female grizzly initiates does not end with her death or relocation. It propagates through her offspring into the next generation and potentially beyond it. Wildlife managers who have worked in the Yellowstone ecosystem for decades can often trace the conflict histories of specific individuals back to maternal lineages that have been interacting with human food sources for 2 or 3 generations. The memory of the settlement is not just in the individual bear. In a functional sense, it is in the family. The range expansion that is currently underway in the Greater Yellowstone and Northern Continental Divide ecosystems is bringing this entire body of findings into a new geographic context that has not been well analyzed from the perspective of what the memory research implies. Grizzly bears have been gradually expanding the boundaries of their occupied range since the 1990s, moving into terrain south and east of Yellowstone, north of the Northern Continental Divide ecosystem into the Canadian border regions, and in isolated cases, well beyond the boundaries of designated recovery areas. This expansion is a conservation success story by almost every metric. The population that numbered fewer than 200 animals in the Yellowstone ecosystem in the mid-1970s now exceeds 700. The Northern Continental Divide population may exceed 1,000. The animals are doing what recovered populations do. They are filling available habitat, testing the boundaries of their range, sending young dispersers into terrain that has not seen a grizzly in decades. The communities in the path of that expansion have been through the social and political disruption of learning to coexist with a large predator that was absent from their landscape for most of living memory. The learning curve is steep, the conflict incidents are real and sometimes severe. The livestock losses are economically significant for small ranching operations. The threat to personal safety in working landscapes, where people move through heavy cover at dawn and dusk during calving and hunting seasons, is not imaginary. And the grizzly bears moving into those new areas are carrying with them the behavioral tendencies and the memory systems of a species that has already, in the core of its recovered range, developed documented patterns of associating human settlements with food. The communities in the expansion zone are not receiving grizzly bears that have no experience with humans. They are receiving, in many cases, dispersing subadults whose mothers were food-conditioned in the core of the range, whose early landscape education included locations where human food was available, and who are entering new terrain with memory systems primed by that early experience to recognize and record human food sources with high fidelity when they encounter them. The practical expression of the memory research in day-to-day conflict prevention terms is something that the scientists involved have been actively working to translate into management guidance, with mixed success and against the background noise of competing institutional priorities and communication challenges. The core recommendation is not complicated, but its implementation requires a sustained infrastructure of behavior change that is difficult to produce in communities that have not historically lived with grizzlies and that have limited experience with the specific attractant management protocols that the research indicates are necessary. The recommendation is this: the window in which a grizzly bear's landscape memory trace, associated with a human food source, can be effectively managed by removing the attractant, is narrow, and it is earlier than most people assume. A bear that has had a single, unreinforced exposure to a food attractant may not form a durable memory trace associated with that specific location. A bear that has had 2 or 3 reinforced exposures to the same attractant in the same location is almost certainly forming a memory trace of exactly the kind the research has documented, and that trace will be recorded with a durability that makes subsequent attractant removal a necessary but insufficient response. The management window is before the 2nd or 3rd visit, not after. After the 3rd reinforced exposure, you are not preventing a memory from forming. You are managing a memory that already exists and that will drive the animal's behavior for years. The bear-resistant container certification programs that have expanded substantially across grizzly recovery areas in the past 15 years represent the most direct policy expression of the understanding that attractant management must happen proactively before memory formation, rather than reactively after a conflict incident has already recorded a location in a bear's landscape memory. The programs have produced measurable reductions in conflict incidents in areas of high compliance. They have also revealed the compliance challenge in sharp relief. In areas where bear-resistant container requirements exist, but compliance is variable, the conflict incident data shows a pattern consistent with what the memory research would predict. Bears are finding non-compliant attractants, forming location memories, and returning repeatedly, even after the non-compliant attractant is eventually secured. The compliant households are getting the protection the containers provide. The non-compliant households are producing memory formation events that affect bears moving across the entire neighborhood, including the compliant households. The social problem of collective action in attractant management, in which the individual cost of compliance is borne by the compliant household, while the individual who is non-compliant produces a conflict risk that is shared across the community, is one of the most significant practical obstacles to implementing the memory-informed management approach at community scale. The livestock protection dimension of the memory problem is where the economic stakes are most direct, and where the political tension between bear conservation and rural livelihood is most acute. The pattern of grizzly predation on livestock in the greater Yellowstone ecosystem, documented in detail by the USDA Wildlife Service's data over more than 30 years, shows something that the memory research illuminates, and that has significant implications for the design of depredation prevention programs. Livestock losses to grizzlies are not randomly distributed across the landscape or across the ranching operations in the recovery area. They cluster. Specific operations experience repeated predation events across multiple years. Specific individual bears are identified as responsible for the majority of losses in specific areas. The clustering is partly explained by spatial proximity to grizzly habitat, by the terrain features that channel bear movements through certain pastures more than others, and by the specific livestock management practices of individual operations that create or eliminate attractant conditions. But the clustering is also explained, in a way that the memory research makes explicit, by the fact that a grizzly that has successfully killed livestock on a specific operation has formed a memory of that operation as a high-value food source that will continue to drive its behavior toward that location until the animal is removed from the population or the attractant condition is so thoroughly eliminated that repeated unsuccessful visits begin to extinguish the memory trace. Partial improvements in livestock protection that reduce but do not eliminate predation events may actually represent the worst management outcome from a memory perspective, because they provide enough intermittent reinforcement to maintain the memory trace without eliminating the conflict. The intermittent reinforcement point is one of the most technically important findings from the memory research, and one that is most counterintuitive to non-specialists. Intermittent reinforcement, the condition in which a behavior is rewarded on some subset of attempts rather than on every attempt, is well established in the behavioral psychology literature as the reinforcement schedule that produces the most durable behavioral conditioning and the most extinction-resistant memory traces. A bear that raids a livestock operation and succeeds on every attempt will form a strong memory trace, but that trace is somewhat more vulnerable to extinction through a sustained period of unsuccessful attempts than the trace formed by intermittent success. A bear that raids the same operation and succeeds on roughly half its attempts because the protection measures are partial and inconsistently applied is receiving exactly the intermittent reinforcement that produces maximally durable memory formation. The implication for livestock protection program design is that half measures may be worse than nothing, because they convert a predictable conflict pattern into an intermittently reinforced one that is harder to extinguish. Complete attractant elimination is difficult and expensive. Partial attractant reduction may produce conflict patterns that are more persistent than the ones that preceded the intervention. The researchers at the forefront of grizzly bear cognitive ecology have been working to build a bridge between the memory findings and the specific management applications that could reduce conflict, improve conservation outcomes, and better protect both humans and bears in the expanding zone of human-grizzly coexistence. The work is technically careful, and the researchers are appropriately conservative about the strength of their conclusions. But the core finding is robust enough, and the evidence for it consistent enough across multiple study populations and multiple methodological approaches, that the leading figures in the field have been willing to say it plainly in peer-reviewed publications, in a way that is not often reflected in the public understanding of grizzly behavior. Grizzly bears remember human settlements for years. They remember specific locations where food was obtained. They remember the seasonal timing of food availability at those locations. They return. They teach their offspring what they know. The memory is not a minor behavioral quirk. It is a central organizing feature of how this species interacts with the human landscape, and it is the feature that every management and conservation decision in grizzly country should be built around. The question of how individual bears differ in their propensity for human food source association, and whether those individual differences are stable and predictable, is one that the ongoing monitoring programs in Yellowstone and the Northern Continental Divide have been slowly building the data to answer. The preliminary findings, still unpublished in their most recent form, but discussed in conference presentations by the principal researchers, suggest that individual variation in exploration tendency, risk tolerance, and response to novel stimuli is substantial in grizzly populations, and that these individual differences are expressed early in life and remain relatively stable across the individual's career. Some bears are more likely to approach novel objects and situations. Some are more likely to avoid them. Some are more likely to persist in exploration in the face of mild, aversive stimuli. The bears that become food-conditioned are not randomly distributed across this behavioral spectrum. They come disproportionately from the high exploration, high-risk tolerance portion of the distribution, and the memory capacity that makes food conditioning so durable, the landscape-level episodic-like memory that the GPS data revealed, appears to be at its strongest in precisely those individuals. The conservation implications of individual behavioral variation in grizzly populations have not been fully worked through, but they point toward an uncomfortable possibility that deserves to be stated directly. The individuals most likely to become food-conditioned and to develop the most problematic conflict histories are also the individuals most likely to be successful explorers of new terrain during range expansion. The traits that make a grizzly bear a bold explorer of novel landscapes, traits that are essential for the population's range expansion and long-term genetic connectivity, are in significant overlap with the traits that make individual bears most likely to investigate and exploit human food sources when they encounter human settlements in those new landscapes. Managing the conflict risk of range expansion is not just a matter of managing the attractants in the expansion zone. It is a matter of understanding that the bears most likely to lead the expansion are also the bears most likely to create the most durable conflict histories when they do. The wolf reintroduction comparison is worth examining here because it offers both a cautionary lesson and a genuinely useful model for thinking about the memory and learning dimensions of large carnivore management. When wolves returned to Yellowstone in 1995, the initial conflicts with livestock were severe, and the predictions of some ranchers about the scale of losses proved accurate in specific cases. But the conflict pattern evolved over time in ways that revealed the role of individual wolf learning and pack-level behavioral transmission in shaping predation risk. Packs that developed livestock predation patterns passed those patterns to new recruits and to offspring. The conflict geography became concentrated in specific pack territories and specific ranch operations in ways that reflected the spatial memory and behavioral traditions of specific packs, rather than random predation distributed across the landscape. The management response that proved most effective was not random lethal removal of wolves involved in livestock predation, though removal of specific individuals and packs was operationally necessary in many cases. It was targeted management, combined with aggressive attractant management on the specific operations that were experiencing repeated predation, addressing the memory and tradition dimension of the conflict rather than treating each incident as an isolated behavioral event. The parallel to the grizzly memory findings is not perfect. Wolves and grizzlies differ in cognition, social structure, and the specific mechanisms through which spatial and behavioral information is shared within and between individuals. But the underlying principle is the same. The conflict pattern reflects the memory and learning history of the specific individuals and groups involved, not just the current distribution of predators and attractants. Managing the conflict pattern requires addressing the memory and learning history, not just the current state of the system. The public communication failure that surrounds the grizzly memory research is, in some ways, the most frustrating part of the story, because the research itself is clear enough and the implications specific enough that better public understanding would produce better individual behavior and better community-level attractant management in ways that would benefit both humans and bears. The failure is not the result of scientific obscurantism or intentional concealment. It is the result of several compounding factors that together produce a gap between what the research shows and what reaches the general public. Wildlife agencies, facing the constant political pressure of the delisting debate and the antagonism of anti-conservation constituencies who would use any information about grizzly risk as ammunition for weakening protections, have been conservative in their public communications about grizzly cognitive capacity and about the durability of food conditioning. The conservation advocacy community, similarly concerned about public perception of grizzlies as dangerous or unmanageable, has not been eager to amplify research that could be misread as making the case for aggressive population control. The research itself, published in journals read primarily by wildlife managers and academic ecologists, has not made a significant transition into the popular science communication channels that reach the general public. The result is a public that understands grizzly bears primarily through the lens of their physical danger and their conservation status, and not at all through the lens of their cognitive sophistication, and that therefore cannot make the connection between its own behavior with attractants and the conflict incidents it reads about in the news. The ranching community in the greater Yellowstone area has developed, over decades of direct experience with grizzly conflict, a practical understanding of the memory problem that in some cases outpaces the formal scientific literature in its specificity and its operational clarity. Ranchers who have worked in grizzly country for generations talk about bears in ways that implicitly acknowledge the memory dynamics the research has now documented. They know that a bear that found a dead calf in a particular pasture 3 years ago will come back to that pasture in the same season looking for another one. They know that a bear that got into a grain bin once will return until the bin is bear-proofed or the bear is dead. They know that the trouble animals are often recognizable across multiple seasons, and that their conflict histories have a consistency that reflects the same location-specific, temporally structured memory that the GPS data captures in formal scientific terms. The translation of that practical knowledge into formal management protocols has been slow and incomplete, partly because the knowledge lives in communities that have not historically been in strong communication with the academic research programs, and partly because the solutions that the practical knowledge points toward, comprehensive attractant management at community scale over sustained periods of time, require institutional resources and regulatory authority that individual ranchers operating alone can. The next phase of the memory research, now underway at multiple sites in the Yellowstone and Northern Continental Divide ecosystems, is attempting to answer questions that the first phase documented but could not explain mechanistically. The questions are fundamentally about what happens in the bear's brain when it forms these durable spatial memories, how those memories are structured and retrieved, and whether there are conditions under which they can be disrupted or redirected in ways that might offer management applications. The neuroscience component of this work, examining the hippocampal and related structures in grizzly bears compared with other ursid species and with other large carnivores with different spatial memory demands, is in early stages and has not yet produced findings that translate directly into management guidance. But the direction it is pointing, toward an understanding of grizzly spatial memory as a distinct cognitive specialization shaped by specific ecological selection pressures and implemented through specific neural architecture, is one that the researchers involved believe will ultimately provide both a deeper mechanistic understanding of the phenomenon and a clearer framework for designing management interventions that work with the animal's cognitive architecture rather than against it. The aversive conditioning programs that have been used in various forms across Grizzly Range to attempt to create negative associations with human presence or human food sources represent the most direct current application of what researchers understand about bear learning, and the evidence on their effectiveness is more nuanced than either their advocates or their critics tend to acknowledge. Programs using rubber bullets, beanbag rounds, trained Karelian bear dogs, and other aversive stimuli to condition negative responses to human proximity or human food sources in individual bears have shown effectiveness in the short term, and with bears that have limited prior food conditioning history. They have shown substantially less effectiveness with bears that have established food conditioning histories, and with bears in which the memory traces associated with human food sources are already well consolidated. The pattern is consistent with what the memory research would predict. An animal with a weak or newly formed memory trace for a human food source location can have that trace disrupted or overwritten by strongly aversive conditioning. An animal with a well-consolidated, multi-year memory trace for a high-value food source is operating on a memory that is much more resistant to disruption. The aversive conditioning creates a competing memory, but the competition between a recently formed aversive association and a multi-year, repeatedly reinforced food association does not reliably resolve in favor of the newer trace. The grizzly bear electric fence enclosure programs that have expanded substantially across the greater Yellowstone area, specifically the programs that provide technical and financial assistance to ranchers and beekeepers in securing attractants with properly energized electric fence, represent a management approach that the memory research strongly supports on mechanistic grounds, and the field data on conflict reduction in operations that have implemented comprehensive electric fence enclosure is among the most encouraging in the grizzly conflict prevention literature. The logic is not just that the fence prevents access to the attractant. It is that the fence, when properly energized, delivers an aversive stimulus of sufficient intensity and reliability to create a strong negative association with the specific location of the attractant. For a bear that has not previously accessed the food source, the fence prevents memory formation associated with successful food acquisition. For a bear that has previously accessed the food source before the fence was installed, the fence may be less immediately effective, but over time can substitute a strong negative memory for the positive one if the fence is maintained and the aversive experience is consistently delivered. The intermittent reinforcement problem applies here as well. A fence that is sometimes energized and sometimes not, which is a common failure mode in practice, provides exactly the intermittent negative reinforcement that may be insufficient to compete with a well-consolidated positive food memory. What the memory research ultimately argues for, in its policy implications, is a preventive, rather than reactive management philosophy across the entire zone of human grizzly coexistence, applied consistently and at community rather than individual property scale, and implemented early enough in the expansion of grizzly range into new areas that the initial contact between bears and human settlements happens in an environment where the attractant management infrastructure is already in place. The difficulty of achieving that in practice, given the political, financial, and social challenges of comprehensive attractant management programs in rural and exurban communities that are simultaneously processing the significant disruption of learning to coexist with a species that was absent from their landscape for generations, is substantial and should not be minimized. But the research suggests that the cost of failure is not just measured in individual conflict incidents. It is measured in the gradual assembly, across the landscape, of a population of bears with detailed, durable, multi-generational memories of human settlements as food sources, memories that no subsequent management intervention will fully erase and that will continue to drive conflict for the lifetimes of the individuals that carry them, and potentially into the generations they produce. The 700 grizzly bears currently occupying the greater Yellowstone ecosystem represent one of the most remarkable conservation recoveries of a large carnivore in North American history. The 2015 population survey estimated the population had recovered to a level not seen since the early 20th century. The animals are healthy, reproducing, and expanding their range in exactly the ways that successful conservation management hopes to produce. They are also in the most heavily monitored carnivore population on the continent, demonstrating a memory capacity that fundamentally changes the terms of the coexistence challenge that the recovery has created. The bears that are moving south and east out of the park boundary are not blank slates exploring an unfamiliar landscape with no prior information. They are animals whose cognitive architecture has been shaped over millions of years of evolution to record and retain exactly the kind of location-specific, temporally structured, high-value food source memories that human settlements provide. They will record what they find. They will return. They will, if they are female and they reproduce, share what they know with the generation they raise. The scientists who study these animals have been saying, with increasing directness and increasing specificity, that the memory problem is not peripheral to grizzly bear management in the 21st century. It is central to it. It is the mechanism through which the contact between an expanding bear population and a landscape saturated with human infrastructure and human food sources translates into conflict patterns. It is the reason why reactive management, responding to incidents after they occur, is insufficient on its own. It is the reason why the specific timing, consistency, and comprehensiveness of attractant management matters in ways that the standard public messaging about keeping a clean camp does not fully communicate. And it is, ultimately, the reason why the story of grizzly bear recovery in the American West is not just a conservation success story. It is a cognitive story, a story about what an extraordinary mind, built by millions of years of ecological pressure in some of the most demanding foraging environments on the continent, does when it encounters the most predictable, most calorie-dense, most reliably located food aggregation it has ever evolved to remember. It remembers, for years, with a precision that surprises the researchers who study it, that challenges the management frameworks built without it, and that will define the terms of human grizzly coexistence for every decade of the recovery that follows this one. The animal crossing the road at the edge of your town at dusk is not wandering, it is navigating. It is consulting a map that was built over years of direct experience and, in some cases, over a lifetime of learning from a mother who made the same journey before it. The question of whether humans and grizzly bears can share the landscape that both now occupy is not primarily a question about bears. It is a question about whether humans can learn to manage the specific cognitive reality of the animal they have chosen, rightly, to bring back from the edge of elimination. The bears have already learned what there is to.